In this example, we've got a multi-span beam that structurally is symmetric. We've got these two shorter outer spans with only EI, a longer midspan that has twice the flexural rigidity, but we don't have symmetric loads. And it turns out because of the support movement, we don't have symmetry in that either, despite the symmetry and the structure and the foundations. So in a previous video, we did a little bit of thinking about how this structure might respond, and we might again guess that we're going to get a sag downwards on the outer edges, will pop up in the middle. That'll mean a counterclockwise rotation of B, a clockwise rotation at C. That would all begin to make sense, right? But let's probe into this a little bit more differently. Apply the slope deflection as an approach to this particular situation, right? And of course, the first step in the slope deflection method is to identify these kinematic degrees of freedom. That the rotation at A is going to be 0 because of the fixed end. The rotation at D is going to be 0. That because support B moves downwards, we know that we're going to get this chord rotation for the left span. We'll get a chord rotation for the middle span, but we will have no chord rotation here in the outer right span. All that's going to be particularly important. Now, in the slope deflection method, it is always the case that you need to be thinking about, do you have sway or do you not have sway? We do. That's the chord rotation. But now you got to ask the question of, is the sway amount of sway known or is it not known? If it is not known, it adds a kinematic degree of freedom that one of these sides becomes a question mark, as opposed to here we know it's not 0, but we can in each case be able to identify just how much exactly is happening. Right? So we have support B moves downwards by 0.01 inches, or rather meters, over that 5 meter length, and because that is a clockwise rotation, that would be a positive chord rotation value, as opposed to what happens on the other span. Then that's counterclockwise, so that's a negative rotation with the sign convention that we're using. Now, if this had been a situation where both B and C would have moved down, that would have, of course, lessened the amount of chord rotation of BC. In other words, we need to use the differential settlement to get the chord rotation value and work that all in. Of course, if that would have happened, then the right-hand span would have had a chord rotation value too. All right, that all seems rather confusing. Replay that segment a number of times. I will say the same thing, but it may start to settle in a little bit more. So in this problem, just to summarize here, we've got a kinematic degree of freedom at B. We don't know how much that rotates. We suspect that that will end up being a negative value because it'll rotate in a counterclockwise way. And then at C, we don't know how much that rotates. We think that will be positive because we think that regardless of what happens, there will be a clockwise rotation at C. Right, now the next part is then to get charging away in the setup of the slope deflection approach. We'll write the slope deflection equation for each member N. Here we have the general expression. It's usually convenient, especially when processing by hand, to go ahead and find the I over L values of each of the members. So I over L of AB and BC and CD. So that's the I over 5 meters, 2I over the 7.5, I over the 5. So again, the two outer spans are similar. Now you could have put the E in here and really made this a shorthand. I don't know why we don't do that in general in the slope deflection equation, because generally when we're modeling these kinds of situations, the E's are the same values for everything. So it would have been a little bit nicer shorthand, and some people will do that. And if you want to, that's just fine. What I do when I do these things is I do the first step, and I get the I over the L's of the members written down, and then I look for commonalities there for a shorthand approach. And I noticed that we had a 5, a 7.5, and a 5 in the denominator. Hey, if that becomes a 15, then there's a ratio of 3 to that 15 business. So that's what I did, was I rewrote this in terms of a denominator that was 15. So there's a commonality, and that allowed then the relative stiffness values to be easily seen, and particularly in this case as integer values. But even if they'd been like 1.5 or something like that, or even 1.67, whatever real number might show up here, I still would do it this way when I'm processing by hand because it just makes it easier. And that means that our k value that we're working with has now been defined. Now this is k without a subscript, just a generic constant, is I over 15 meters. The units really do matter. You got to be real careful about this, especially in the SI system, to be very thoughtful and careful. Why? Well, let's see what happens. The I value is 200 times 10 to the 6th millimeters to the 4th over now 15 meters when you put the L value, or the thing that's reflecting the L value in there. Right, now that's not a particularly convenient set of numbers. Now where did I get the 200 times 10 to the 6th? That was in the problem statement. Notice that E value 150 gigapascals is going to be important here in a moment too. Now just looking ahead, we've worked some other slope deflection problems where we just left it in terms of EK. We didn't worry about all these numbers. Why are you now so focused on starting to work this out? And it's all going to be about the support movement, and we'll see that here in just a moment. Right? No pun intended. Alright, so let's convert this over into meters to the 4th so we get a little bit more commonality of things. And you'll have 10 to the 12th millimeters to the 4th in 1 meter to the 4th. And that will then turn out to be 200 times 10 to the minus 6th meters to the 4th over 15 meters. Right, now that will come into play here in just a moment. What I'm really setting up is kilonewton meters for a calculation. And I'm going there because we're going to come along and get the fixed end moments. Now again, recall that we had distributed loads all the way across the entire span. So we look up that equation for those fixed end moments associated with that. That's plus and minus WL squared over 12, negative on the left side, positive on the right when you're using the clockwise sign convention, and you get the minus 166.7. That's of course really repeating 666. Same thing on the other one. Notice units kilonewton meters. We have the 80 kilonewtons per meter times meter squared to get there. Right? No transverse load on the middle member. Yes, there's the support settlements. We'll get that here in just a second. And then we'll have the fixed end moments on the outer span, outer right span, different magnitude of the load, so of course slightly different fixed end moments. Again, note the units kilonewton meters. I keep drawing that out because look what's going to happen here, that we've got a known value of the chord rotation. So we want to go ahead and get a total number out of all this. Again, we might not have to with the E in there if we were clever about how we, oh yes we do, because there's no, although there's an E in the other terms, there's no E over here in the fixed end moment. We're dealing with a real number here. We need to have a real number on that one also to get an answer. Alright, so let's work out what 6EK psi AB would be. This is 6EKAB, right? And that is going to be then 6E times, well, KAB is 3K times our psi AB value. And that then, now this gets long, we got 6 times 3, that's 18. We have 150 gigapascals, which is 150 times 10 to the 6th kilopascals, or kilonewtons per square meter. You're probably going to need to work through that units to make sure you're comfortable with that. Giga is 10 to the 9th. And then we got our I value, right, the K of 200 times 10 to the minus 6th meters to the 4th over, this K was based upon I over 15 meters. Again, gotta watch these units. Right now we got kilonewton meter to the fourth over meter cubed, or kilonewton meter. Good, because psi is a radian, so in effect unitless. So we're going to end up with kilonewton meters, which we like. That's the moment. So this 6ek psi is going to turn out to be a positive 72 kilonewton meter. Right? Likewise, we want to do this for the outer span. 6ek BC psi BC, that's going to be equal then to 6e. I said outer. That was not correct. We're in the middle. That's the other chord rotation. CD is the outer one. 6e times 4k times psi BC. Right? And so that's going to be then equal to 4 times 6, 24. We get the 150. Notice the 10 to the 6 and times 10 to the minus 6 goes away, so I'm just going to write that as 150 now, since we've shown all that work over there. And I'm not going to show the units either at this point. And we got that chord rotation in radians value, and that's going to give us now a fixed end moment term here that is negative 64 kilonewton meter. Now note, that's going to be the same on either end, because that's associated with a fixed beam that has been swayed a known amount that by that delta. And notice for AB, that would end up being moments that, positive sign convention would say that's supposed to be like that. And you say, well, but that says plus 72, and that's not the way the hex. It doesn't have to be opposite. Guess what? We take care of the minus sign right there. So that's a little weird and a little flip-floppy, and you have to be a little careful on how you think about all that. Some people would have put the minus sign in a different place and would have handled this in a little bit different kind of way. This is a positive chord rotation, right? Clockwise chord rotation, and you end up actually counterclockwise moments. And again, that's where the minus sign shows up there. All right, so that's the setup. That was kind of a long setup with all the explanation that goes along with it, but there you go. Now we're ready to charge off on the next steps.